Hi, this is Harshit Patni, roll number 201501101107, and I'm here to present the Science 2 Project Phase 2 report. The assigned molecule to me was 3DNL underscore A.pdb. All the codes that was used to run the project is available on this drive link. So in the first phase, I generated a GIF of the trajectory of our SMD simulation, which was visualized in VMD. These were the steps which were followed in the phase 1. Now coming on to phase 2, first of all I will explain what is Zarinsky equality. So Zarinsky equality is an equation in statistical mechanics that relates free energy differences between two states and the irreversible work along an ensemble of trajectories joining the same states. In thermodynamics, the free energy difference between the two states and A and B is connected to the work done on the system through the inequality del F less than equal to W, with equality holding only the case of quasi-static process, that is when one takes the system from A to B infinitely slowly. The equation is also obtained from another theorem known as Crookes fluctuation theorem, and the equality is as follows: e to the power minus del F by kt equal to e to the power minus W by kt, where W by kt is the average work done over all the trajectories. Similarly, the equality is given by exponential of the change in F divided by T and average of exponential of W of T divided by T. The right hand side of the equation can be expanded in terms of so-called cumulants. So on expanding it in terms of cumulants, we get this equation where cumulants up to second order are shown. The PMF estimation is done using the three different forms. First is FEXP, which is equal to minus T of log of average of minus W of T, the exact form. And the second equation is F1 equal to average of WT, which is first order cumulant. Third equation which we are using is F2 equal to average of WT minus 1 by 2T into the variance of WT, which is known as second order cumulant. The script used to calculate the estimates and the store is stored in the cumulants.tcl file. Finally, all the three estimates are plotted together on the same plot. Now coming on to the steps followed in the phase 2 of the project. So after generating the trajectory in the phase 1 of the project, the system analysis of SMD trajectory is done. Since pooling the velocity of trajectories is very high, and thus we reduce the velocity for generating the new trajectories. 3 trajectories were created with velocity of 0.01 angstrom per picosecond and were stored in a file named da.dat. Each trajectory is present in the da underscore smd underscore tcl.out file. Each trajectory had 20,001 lines, as the total time is 100 picosecond and time step is 0.1 picosecond. Similarly, following the other steps and creating da.dot file, then loading the trajectory into VMD, we use load_traj.tcl script, and the row numbers are from 1 to 20,001. The first plot was made using the script plot extension time.tcl file, which creates 2D graph with x-axis as time and y-axis as extension between the constraint points, and constraint in smd.tcl. Fix the initial position at origin and pulling atom at coordinates 0, 0, 13, and this means that the initial distance is 13 angstrom. For the next plot, force against extension for all trajectories using the script plot force extension.tcl is used. For calculating the work, we run the following commands in the VMD TK console, and the work done is now calculated after the executing above scripts using the script calcwork2.tcl, and the plot is made using plotw.tcl. The graphs were obtained as follows. The first graph was obtained between the extension against the time. As seen, the graph is almost linear in time with y, with intercept as 13 as the initial distance. The second graph was plotted of force against extension, and the graph clearly shows the fluctuation in the forces. The plot is of work done against extension and shows that maximum range is about 150. The third plot is here. Then the fourth and final curve is the free energy PMF versus extension. So three graphs were plotted on the same plot, and the three graphs are also here individually. Now comparing my findings with the other people, I compared my findings with two people, Harshit Mahajan and Satyam Mittal. So the first graph is extension versus time. This is the graph of Harshit Mahajan and this is the graph of Satyam Mittal. The observation is as follows. The extension versus time step is linear for Satyam Mittal's molecule, as we can see clearly here. Whereas in Harshit Mahajan molecule and my molecule, the distance is linear with time, but there are some fluctuations. For second graph, force versus extension, the observations are as follows. The force versus extension curves are almost the same for Harshit Patni, Harshit Mahajan and my molecule. Satyam has plotted his molecule by scaling the axis, thus his plot appears to be zoomed in. Third is work versus extension. This is the graph of Harshit Mahajan and this is the graph of Satyam Mittal. The work versus extension shows the uniform relation in case of Harshit's molecule and is almost the same for two trajectories in his molecule, but Satyam molecule shows fluctuation in the trend. Fourth is the PMF calculation graph. In PMF, in case of Satyam's molecule, shows the exponential and linear trajectories very close, but they are far apart in my molecule and Mahajan's molecule. The inferences from above graphs are as follows. The change in free energy is same regardless the path taken, but can only be equal to work done when its cause is static. So if we want to change in free energy, we can only find it through Zarinsky equality. The limit of an infinitely slow process, the work W performed on the system in each realization is numerically the same, so the average becomes irrelevant and the Zarinsky equality reduces to thermodynamic equality del F equal to W. In general, however, W depends upon the specific initial macrostate of the system, though its average can still be related to del F through an application of Jensen's equality. The three curves in the output are the different approximations of the same Zarinsky equation. Thank you.